Okay, yeah. Welcome everyone. Today, in the first talk, we will have Liz Tatum from the University of Bonn. She will tell us about applications of equivariant Brown-Gitler spectra.
Uh, Yeah, thanks, Guchuan. And yeah, thanks for inviting me. It's really nice to be here. Yeah, so I guess before I talk about equivariant Brown-Gitler spectra, I want to start by like sort of reviewing the seat. Oh, sorry, I guess my camera stopped working, but yeah, I guess as long as you can hear me, that's probably good. Great. Okay. Let me know if you can't hear me. Sorry about that. Anyway. Before I start talking about like the applications of equivariant Brown-Gitler spectra, I want to first like recall the non-equivariant story. And so first just starting with like some very broad motivation for why people are interested in Brown-Gitler spectra. And so I should say this is just sort of like one sort of like thread through which you can tell this story. There are lots of really cool applications of Brown-Gitler spectra. They were originally constructed in order to study emergence of manifolds. But today I really want to focus on their usage in terms of atom spectral sequences. So I'll just sort of stick to that thread. So just like some very, very broad motivation is that we would all really like to understand the homotopy groups of the sphere better. And so atom spectral sequences are like one family of tools that we can use to approach this problem. And so just to recall what an atom spectral sequence is, you can choose a ring spectrum R, then there should be an R-based atom spectral sequence. Its E1 page is going to take the homotopy groups of R smashed with itself many times, and it should converge to the homotopy groups of the R completed sphere. So that's the E1 page. So then you would want to know what the E2 page is. And so sometimes you can sort of get to the E2 page for free. So specifically, if R smash R is just a sum of copies of suspensions of R itself, then we say that the ring spectrum R is flat. And in fact, you can show that if your ring spectrum R is flat, then the E2 page is going to have this nice algebraic description as like X groups over R star R. So for example, if R is HC mod P, the mod P Annenberg-MacLane spectrum, that's the classical atom spectral sequence. So that's probably the most familiar one. So it's E2 page. We write A star, the dual standard algebra for HC mod P star HC mod P. And we're taking the X of the dual standard algebra over FP. And that should converge to the homotopy groups of the P completed sphere. Then another very classical one is to take MU, that's the complex Mortison spectrum, or it's usually easier computationally to like take its summand BP, the Brown-Petersen spectrum, or sorry, it's a summand of like the P local MU. And that's the Adams-Davikov spectral sequence. And again, MU, BP, they're flat. So you can write the E2 page as this X group. But even though like it's super great that you know these are X groups, we can write them you know down algebraically. These are still very, very complicated. We don't have like a closed form description of these. And then furthermore, of course, this is only the E2 page. You have to, you know, compute further differentials to get more information. So even though these have been like very, very productive, you know, atom structural sequences, it's also been really helpful for people to consider like other choices of ring spectrum are. So another example that's been very useful is to take R to be KO. So this is connective real K theory. This is also often denoted BO, depending on what literature you're looking at. And that's like usually that's most useful at the prime two. At odd primes, you can take KU. This is connective complex K theory. This is also sometimes denoted BP1. I guess BP1 is a summand of it. So then why are these like good choices of so like what's really nice about these atom spectral sequences with KO and KU? So one really nice thing is that they highlight V1 periodicity. So like it's expected that it's expected that the stable homotopy groups of the sphere are organized into these Vn periodic patterns. And the idea is that the nice thing about the KO and KU based atom structural sequence is that it highlights like the V1 periodic portion of that. Okay, then they also collapse at the E2 page, certainly not for the whole spectral sequence, but like in a good range. So once you get to the E2 page, you already have a good deal of information. And these properties allow you to get lots of cool results. So one of those would be the telescope conjecture at height n equals 1 for the prime 2 was proved by Mahowald using the KO atom structural sequence. And of course now that's been disproven at all the other heights. But it seemed to work out nicely, I guess, at the height where it worked. Then what else? So you can efficiently compute pi star S2, so like the homotopy groups of the sphere localized at 2, through the 40 stem using a KO atom structural sequence. And this is not like, I don't think the first way that most of those groups were computed, and there's lots of other ways to compute them, but I think this is sort of like the most efficient way to do it in those degrees. And so this was like first due to like, I think up into the 20s, due to like Davis, Lovett, and Mahowald in like the 1980s. And then more recently, Beaudry, Behrens, Bhattacharya, Culver, and Shu were able to extend those computations up through the 40s. Then, yeah, there's lots of different applications of these. I think another fun one is classifying stunted lens spaces. So that was using the KU-based atom structural sequence by Gonzalez. Yeah, but okay, so these have all these nice applications, but what's tough about them is that the spectra KO and KU are not flat. So just to get started going with these, you don't have the algebraic description of the E2 page. But we sort of have the next best thing. It's not so bad. So like KO smash KO splits as a sum of finitely generated KO module spectra. So you don't just have a sum of copies of KO over here, but you do have a sum of copies of KO smashed with like some finite spectrum. And sort of the same thing for KU. KU smash KU splits as a sum of finitely generated KU module spectra. And this is due to Mahowald and Kane. And then what one can do is use these splittings to understand the E1 page of like the respective atom spectral sequence. Okay, so now I'm going to move on to talking about just like the non-equivariant Brown-Gitler spectra, because I guess I should say like these finitely generated KU module spectra, for example, they're built out of Brown-Gitler spectra, and that's where those will come in. But first, I just have to say a little bit about the dual-Steenrod algebra. So you can fix the prime P, and let's just let H denote HFP to make things a little easier. So then the dual-Steenrod algebra is H star H. At the prime 2, that should be this polynomial algebra. And at odd primes, you'll have the polynomial piece, tensor with an exterior piece as well. So then what you want to do is define a filtration called the weight filtration, where you assign to the monomial Cn, weight p to the n, and you assign to the monomial tau n, the weight p to the n. And then the weight of xy is going to be the weight of x plus the weight of y. So like it's an additive filtration. Okay, so then that will allow us to define Brown-Gitler spectra. So the Brown-Gitler spectra, they were originally constructed at the prime 2 by Brown-Gitler, unsurprisingly, and then this was extended to odd primes by Cohen. So there are more things you can say about Brown-Gitler spectra, but the relevant properties for us today, in this talk, are that there exist finite spectra, which we'll call B minus 1 of K, K and N, and this family of spectra has the property such that the homology of like the kth spectrum here should have, or it should consist of all the monomials in the dual-Steenrod algebra. Thank you, Doug. That's Ralph Cohen. Yes. And having weight at most pk. And then so these have like these have like homology that realizes like the different like steps of this weight filtration. And then furthermore, they're going to come along with some nice maps. So there will be a map from the Brown-Gitler spectrum to the Mahowald-Kane spectrum for each K. And then these like pairing maps so that if you take like this K smash mth Brown-Gitler spectrum, you should land in the K plus mth Brown-Gitler spectrum. And that's going to commute if you first took these maps to the Mahowald-Kane spectrum and then did the like usual multiplication on the Mahowald-Kane spectrum here up to homotopy. So then one can also define integral Brown-Gitler spectra. So the integral Brown-Gitler spectra, these are sort of like the first of the generalized Brown-Gitler spectra, and you can define like some analogs of these at higher heights and things like that. But I think for today's talk, we're just going to look at the integral ones. So the thing to notice here is that the homology of HZ, the Eilenberg-MacLane spectrum for the integers, is contained in the Joule-Steenrod algebra. So what you can do is go ahead and apply the weight filtration to this as well. And then Shimamoto and Cohen-Davis-Gorst-Mahowald were able to show that there's going to be like finite spectra sort of realizing the weight filtration in this H star HC. So the theorem is that there exist finite spectra, which we call B0 of K, such that the homology of B0 of K is what we would like it to be. They're going to also come along with these maps, but now into the integral Eilenberg-MacLane spectrum, but they'll have analogous pairing maps, and we have this analogous diagram should commute up to homotopy. Okay, so now to tie this back in with the splittings that we were interested in, you can show, like it's pretty straightforward to show that like on the level of homology, HC smash HC is going to be isomorphic to H star HC tensor with the homology of like the appropriate Brown-Gitler spectra suspended and summed up. So like on the level of homology, this is the kind of splitting you're looking for because you're saying that like HC smash HC is like HC, well, tensored with this like finite spectrum. And then likewise for KU smash KU. So I guess I should say for HC smash HC, you use like these original Brown-Gitler spectra. For KU smash KU, you use these like height, these integral Brown-Gitler spectra. And likewise for KO smash KO, you use integral Brown-Gitler spectra. So then the question becomes whether you can actually construct spectrum level splittings of these. And indeed, Mahowald and Kane showed that up to P completion, you can indeed like realize these on the level of spectra. Okay, and then I guess what I want to do next is just like sketch how or like one method of constructing the KU splitting because it's going to be similar to the one that we do equivariantly. But before I do that, are there any questions? Oh, okay, no, sorry, I'm just gonna see. I think my Zoom is like slightly frozen. Huh. It's weird. Okay, sorry. I think it's unfrozen, but let me know if like things aren't lining up. Okay, so I want to sketch a construction of this like KU splitting. And I should say like the HC smash HC splitting is like very similar, but just like a lot easier. It's sort of a nice like sort of like form of example, and then KO smash KO is also similar, except in the opposite direction. It's like, you know, computationally more difficult to deal with. Okay, so before like sketching the construction of the KU splitting, I want to first we're going to need some tools from like the category of KU modules. So let's just take X and Y to be like any old KU module spectra. Um, so then the first thing we want to look at is like the KU relative smash product. So this is going to be defined to be the co-equalizer of if I take like the action of KU on X and then the action of KU on Y. So this is just the smash product in this category. Then we also want it to be able to take like the KU relative like homology of a spectrum X. So we're going to just define this to be like the homotopy of H smash X, but KU relative. Okay, then what that does for us is that gets us an H-based, we can define an H-based atom spectral sequence, but like in the KU module category. So this is going to have as its E2 page, X over the dual Steenrod algebra, but KU relative, of the homology of X, the KU relative, the homology of Y, the KU relative, and will converge to maps from X to Y, but KU module maps. Then one can show that the KU relative like dual Steenrod algebra is going to be E of 1 star, where this is like the dual of E of 1, which I don't want to get like too much into this, but I think maybe just the thing to know here is that like E of 1 is an exterior algebra on Q0 and Q1, so two Milnor primitives contained in the Steenrod algebra. So this is like a pretty manageable algebra to deal with. It's just exterior on two generators as opposed to the Steenrod algebra, which is a lot. Then, okay, in particular, we're going to be interested in like a particular one of these atom spectral sequences. We want to take X to be KU smash with B0, okay? And Y to be KU smash KU. Then furthermore, we want to use the fact that if Z is like any spectrum, and you take like the KU relative homology of KU smash Z, that's actually going to be isomorphic to just the homology of Z. So then looking at our atom spectral sequence for X being KU smash B0K, Y being KU smash KU, this just reduces to X over E of 1 of the homology of B0K and the homology of KU. And then finally, we want to use the fact that there's like an equivalence of categories between finite type E of 1 modules and finite type E of 1 dual co-modules. This isn't strictly necessary, but I just find that like modules are a little easier to deal with than co-modules. Okay, so then you're left with an atom spectral sequence whose E2 page is just this X over this small exterior algebra of the homology of B0K to the homology of KU. And it should converge to KU module maps from KU smash B0K to KU smash KU. So the idea here is that you want to find like a class that lives on this E2 page and then lift and show that it survives the atom structural sequence to get like the maps that we need to build this equivalence. So to be like more specific, there's an E of 1 module isomorphism from like a sum of appropriate suspensions of these Brown-Gitler modules over to the homology of KU. So then what you can do is take like the map phi k for each Brown-Gitler spectrum and think of it as being like a class that lives in the E2 page of this atom spectral sequence. So the strategy is to show that each phi k survives the atom spectral sequence because if it does, you get like these lifts to the level of spectra with a property that the homology of those lifts adds up to be an isomorphism. So then you get that like your lifted maps give an equivalence like up to p completion. So yeah, so at that point, you're reduced to having to like compute like this X term and show that there are like no Adams differentials are possible. And so that takes like some work, but is maybe like more manageable than things started out. But yeah, are there any questions about like that or like about that strategy? Okay, then I'll move on to talking about like the C2 equivariant analogues. So now the idea is we want to see like how much of this story we can retell in the C2 equivariant setting. Oh, and maybe I should mention about the, sorry, before I move on, about the non-equivariant setting. Like there are a lot of different ways to like approach this construction of of KU smash KU. In the non-equivariant setting, like for example, if you look at Kane's like original construction of this, it's like very much like inductive. You build, you sort of build the maps by hand using like these pairing maps of these Brown-Gitler spectra. And there are like various other ways to do it, but I think that this is sort of the one that translates the most easily to the like equivariant, the C2 equivariant settings. That's like why I wanted to recall it. Okay, so the first thing to ask if you want to do things C2 equivariantly would be like, do we have like analogs of all of these sort of spectra? And the answer is yes. So we're going to replace HF2. Oh, and I should say from now on, let's fix the prime to be 2. Right, so the analog of HF2 will be the Eilenberg-MacLane spectrum for the constant C2 Mackey functor F2. The analog for HC will be the Eilenberg-MacLane spectrum for the constant C2 Mackey functor for Z. Then there's K, so then the analog of KU is going to be KR. So this should be like the equivariant connective cover for a T real K theory. Then KOC2, I think there are like different I guess there are different analogs that you can take for KO depending on what you want to do. But for our purposes, we would want to take this KOC2, which is the equivariant connective cover of the K theory of C2 equivariant real vector bundles. Okay, then we want to see like how much of the non-equivariant story we can retell in this setting. So let's start with the C2 equivariant dual Steenrod algebra. Because if we want to have Brown-Gitler spectra, we'd like to be able to do some sort of analog of like this wave filtration all on the dual Steenrod algebra. And in fact, it turns out you can do that like quite naturally. So C2 equivariantly, the dual Steenrod algebra turns out to just look a lot like actually the dual Steenrod algebra at odd primes in the non-equivariant setting. So you have like this polynomial, piece, and then these tau i's are supposed to be like equivariant lifts of the exterior ones from the Steenrod algebra. Then you have like a similar relation. You have similar relations here, but like it's a bit more complicated because you're working over HF2 star rather than F2, and this diagram here is supposed to be HF2 star. And so maybe something to like note here is that in the C2 equivariant setting, we're grading in ROC2. So we need to keep track of topological degree, but then also motivic weight as well. So this is sort of grading on like the number of sign representations. And then this is like would be like the number of trivial representations plus the number of sign representations. Okay, but for our purposes, maybe the thing to note here is that we still have these CIs and these tau i's as generators. They're just over something a little more complicated. So we can go ahead and like just define the same weight filtration on here. And indeed, there's a here. And indeed, we have C2 equivariant Brown-Gitler spectra. So there's finite spectra such that the homology of, or like the C2 equivariant homology of these Brown-Gitler spectra is like composed of monomials having like the appropriate weights in the C2 equivariant dual Steenrod algebra. And they come along with sort of analogs of these pairing maps that we would hope for. So that's the like the mod P Brown-Gitler spectra. Then there's also C2 equivariant integral Brown-Gitler spectra. And again, these are finite spectra with the property that their homology is consisting of monomials in the homology of this integral Eilenberg-MacLane spectrum that has weight at most pk. and they're going to come along with these pairing maps that we would hope for. So far, things sort of go as you would like hope for them to. Okay, then what about splittings? So you can show, again, it's like pretty straightforward to check that on the level of this like HF2 star homology, you get the splittings that you're looking for HC smash HC, KR smash KR, KOC2 smash KOC2. Okay, and then what's a little trickier is to figure out whether we can lift these equivalences to the level of spectra. So far, we've been able to confirm that this works for HC and that this works for KR slash KR. Then the next step would be to try it for KOC2 slash KOC2. But for now, I'll spend like the remainder of the talk sketching the construction of the KR splitting. But I guess, are there any questions? Okay.
You mentioned there are a couple of different connective versions of C equivariant KO. So does that affect the homology computation here?
I think that it would. I guess I wasn't thinking specifically of like so I guess the connectivity that we're taking is the one where you want to take a connective you want it to be a connective cover on both the underlying and the C2 fixed points. So yeah, I would imagine if you took like a different one, you would get a different homology.
Mm-hmm. Yeah, but so that sort of suggests that this would be the right thing to try. Yeah. Thanks.
Oh yes, yeah, I think so. That's why we picked it. Yeah. Other questions? Okay. Thanks. Okay, so constructing the KR splitting. So the sort of like the overall approach is like exactly what we went through for KU modules, or sorry, for KU smash KU, like the non-equivariant. But this time I'll get like, more, I'll try to get a little more into like the computation of it. So constructing the splitting. We'll let modules over KR denote the category of KR modules. And in this category, we can consider an atom spectral sequence, exactly analogous to the one we considered in the KU module category. So now we're looking instead at like the X over this E of 1 star, which I've tried to write slightly differently to show that it's the equivariant analog of E of 1. We're looking at the HF2 star homology of this equivariant Brown-Gitler spectrum and the HF2 star homology of this equivariant KR. And this is going to converge again to maps from KR smash B0K to KR smash KR. And then maybe something else to like notice about this atom structural sequence in contrast to the non-equivariant setting is that we're grading on 3. It's going to be graded in 3 degrees. So S here should be STEM. F should be atoms filtration. And so those we both had in the like non-equivariant version. But then this W here is also the motivic weight. So that's keeping track of the number of sign representations. And the atoms differential, it does the same thing on STEM as it would in the non-equivariant. So it subtracts 1. It does, oh, sorry, this should not be a 1. This should be an R. Right, it increases the atoms filtration by R, and it preserves the motivic weight. Something to note is that this map phi k that we want to lift lives in in degree 0 on the E2 page. And again, if phi k survives the atom structural sequence for all k, then like the sum of these phi k's is going to give an isomorphism on HF2 star homology. And then that's enough to tell you that this phi twiddle will be a 2 complete equivalence. And we would have an analog, like an equivariant analog. So what's left to do is that we need to show for all k. First, we need to show that phi k is not the target of a differential. So that part's very easy because phi k lives in degree like in filtration 0. The atoms differential increases the filtration and nothing lives below atoms filtration 0. So that's for sure not going to be the target of a differential. Okay, but then what about the other bit? We need to know that phi k is not the source of a non-trivial differential. And that turns out to be a bit more work. So in order to show that phi k is not the source of a non-trivial differential, what we'll do is try to like get a handle on this E2 page. So understand like where the classes are living and things like that. So maybe the first thing so we'll want to like break this down into like more manageable pieces. So maybe the first thing is to recall that the HF2 star homology of KR is actually isomorphic to this like sum of suspensions of, and sorry, this should be the homology of this these Brown-Gitler spectra. So it's going to, oh, sorry, my pen just ran out. But it's going to suffice to just compute the homology. It's going to suffice to just compute the x terms of the homology of B0k, B0m for all k and m, because then you could sum them up and get this E2 page. So like in order to approach this problem, we want to start by like understanding the E1 module structure like of these Brown-Gitler spectra. So I just want to say like a little bit more about E of 1. So E of 1 here, it's going to be generated by these Milnor primitives. So it's exterior, and it's contained in this complicated standard algebra, but it really is just this exterior algebra on two generators. And you can see here that the Q0 and Q1, you have to keep track of what they're doing to the topological degree and also the motivic weight. And because we're like grading on homology here, Q0 and Q1 are going to decrease topological degree and motivic weight. And then we're going to be particularly interested in like a certain class of E of 1 modules, which are the lightning flash modules. So L of 0 is defined to just be M2 or HF2 star. Then L of k for each k is going to be generated by these k generators with certain relations. But I think maybe the easiest way to like think of them is to sort of look at the pictures. So L of 1, we have x1, Q0 x1 is non-trivial, Q1 x1 is non-trivial, but Q0 Q1 x1 is trivial. And then you could look at L2, we have Q0 x2, Q1 x2 equals Q0 x1, Q1 x1 is non-trivial, but if you did Q0 Q1 to anything, you would get 0. And so why do we care about these lightning flash modules? Well, it turns out that the homology of these Brown-Gitler spectra can be broken up into a sum of like a suspension of some lightning flash module and many like some copies of E of 1 star. So this is basically breaking up the Brown-Gitler spectra into this like lightning flash module and some sort of like free and injective pieces. So we were saying that we were interested in computing x over E of 1 of the homology of B0k and the homology of B0 of m. So now like using this fact, we can break this up. And sorry, I think I got my indices slightly off here. But the point is that we can break this up into like 4 summands where we have this one that consists of the lightning flash that only has lightning flashes. And then everything else has an E of 1 term. And we can show that E of 1 star is injective and projective. So what that means is that like all of these x terms are going to be concentrated in Adams filtration 0. And it's not going to be possible for any differentials off of there to hit this lightning flash term. So in fact, like we know that like these summands are just going to collapse immediately in the atom spectral sequence. So we can just completely ignore those. So all we're really left to compute is x over E of 1 of these lightning flashes. Oh, sorry, question. Oh, sorry, I forgot to say what the indexing was. Oh, yes, thank you for already answering that. Yeah, 2m is topological dimension and the second m is motivic weight. Yeah, thanks. Sorry, I forgot to mention that. Any other questions? Okay, so now we've reduced the problem to computing this particular x term. So like our strategy for that is going to be to start with this short exact sequence. So for all k, the lightning flash modules have this nice short exact sequence where if you take like a suspension of the k minus first lightning flash module, that'll inject into the kth, and then the quotient is e of 1 mod mod e of 0 dual. And we can actually sort of see that as a picture. So I've just drawn the one for like, we start with L of 1, we map into L of 2. So we're hitting all of these. And then you can sort of see visually that like what's left over is this e of 1 mod mod e of 0 dual. And so like sort of morally what's happened here is like you had e of 1 and you've like quotient out by e of 0. So you would have had e of 1 but you've gotten rid of like the of everything except this q1. Right, so this is the short exact sequence we want to use. So step 1 is to use the long exact sequence induced by applying x over e of 1 star of m2 to then inductively compute x over e of 1 of m2 L of m for all m. So inducting on the right variable. Okay, then we're going to use, so like recall that like m2 is equal to L of 0. So step 2, you're going to use the long exact sequence induced by x over e of 1 star on the right variable to inductively compute this x over e of 1 of L of k, L of m for all k and m. So I think, so I guess at this point, like I think that the computations get like, and the bookkeeping gets quite messy, but like the sort of the idea itself is like, I think very like nice and simple. So I think for the remainder, I don't want to get like too much into the bookkeeping itself. I'll just like show some pictures to try to give like a general idea of what sort of things happen with this inductive computation. Okay, so starting with computing x over e of 1 star of m2 L of m. So the base case is x over e of 1 of m2, because that's what happens when m is 0. And lucky for us, this was already computed by Q, Hill, Isaacson, and Ravenel. And so this x over e of 1 star of m2, it's very complicated, but it does sort of split into these two pieces, which we've sort of been informally calling like the positive piece and the negative piece. And so where this is coming from is that M2 is a square zero extension of M2R. So you can show, which is like the R motivic M2. So you can show algebraically that like x over e of 1 of M2 should split actually the sum of like this x over e of 1R of like this R motivic M2. And then this NC is the negative cone also over xd of 1R. So there's definitely, I think, some like nicer diagrams in this paper of Q, Hill, Isaacs, and Ravenel, but just to give a rough idea, this is like the positive part over here. This is the negative part over here. And like for this talk, I'll just sort of focus on showing what happens in the positive part. But the negative part is like similar, just more complicated. And I think this is sort of messy to look at, but I think it's helpful to compare to the non-equivariant setting. So non-equivariantly, x over e of 1 of FP is just FP adjoint V0 and V1. And you can sort of see that here. So going up this way, we have 1, V1 squared. Going up this way, these are V0 towers. And then going off to the left, these are like row multiplications. And so those don't get like picked up in the non-equivariant part. Okay, so that's our base case. But we also need to know about x over e of 1 dual of m2 e of 1 mod mod e of 0 star. Well, fortunately, you can do a change of rings here. This is now x over e of 0 star of m2. And that turns out to be like a much simpler version of this x over e of 1 computation. And so non-equivariantly, you would just have a V0 tower. Equivariantly, there's some rows involved. Okay, so those are the pieces. Now you can put it together and induct. So let's do just the example of like the positive piece of x over e of 1 star of L of 0 to L of 1. Okay, so this is our like n equals 0 piece. This is the x over e of 1 mod e of 0 dual. Then we're looking at a long exact sequence, so there's a differential in that long exact sequence. But fortunately, that turns out to be 0 for degree reasons. So you end up just putting these together, and there should be like a V1 extension here. Okay, then you can keep going and show by induction that x over e of 1 star of any of these lightning flash modules, like up to V1 extensions, is just going to be a sum of like the 0th one suspended with a bunch of these x over e of 0 towers added on. And what's nice about this is that this is actually giving you the E2 page for the spectral sequence converting into KR star KR. And this spectral sequence collapses at the E2 page for degree reasons. So sort of as a side effect of this, you can have a way of like inductively computing KR star KR. Okay, so that's like the right-hand side induction. Now we have to induct on K to get xd of 1, L of K, L of M for all K and M. Okay, so again, the base case K equals 0. We already have, that was exactly what we were doing here. Then we have the other piece, x over e of 1 dual, e of 1 mod e of 0 star to L of M. We can do a change of rings again, but there's a shift because we're over on sort of the wrong side, quote unquote, here. But this ends up just being a shifted copy of this xd of 0 dual. Okay, then I think I'm almost out of time, but just a small example of, so it's sort of, there's sort of, this part sort of breaks into two pieces. So computing x over e of 1 star for k less than or equal to m kind of all looks the same. So this piece here, this is our x over e of 0 star piece. And there are differentials that go from the x over e of 1 of L of 0, L of 2 over, or sorry, L of 1, L of 2 over. And we know that these differentials are non-trivial because we can compute Homs over L of 1, L of 2 by hand. So you know that like this first differential off the 0 line has to be non-trivial. And then by V0 linearity, these will also all be non-trivial. So you can get x over L of 1, L of 2. Then you want to continue and do this also for k greater than n. So let's do the example of x to L of 2, L of 0, plus this shifted x over e of 0 dual, telling us about x of L of 3, L of 0. And it's a similar situation. There's like this differential and all its V0 multiples could be non-trivial. And so here we can't really use the argument of like computing Homs by hand, but what we can do instead is do a trick. You can sort of like just, okay, suppose that this differential was trivial, then you could try inducting on the right-hand variable to get back up to x of L of 3, L of 3. We already know what that is. And so that's enough to tell us actually this differential has to be non-trivial. And so you're left with this. And so that's just sort of like a cartoon of how we do these computations. But the conclusion is that like we can inductively describe the summands for our atom spectral sequence, x over e of 1 from the homology of B0K, homology KUR, converging to this. So then at that point, you need to do some analysis and see that actually there are no differentials. And so there's a lot of bookkeeping that goes on, but you don't have to do anything too fancy. There's sort of like two main arguments that you use. So one is that like you can never have a differential from a V1 or V0 torsion class to hit a torsion-free class. And the reason for that is that the differentials are like V1, V0 linear. So this would cause a contradiction. Then the other thing you have to do is like some careful analysis of the motivic weight and degree. So I think maybe something I really should have mentioned and did not carefully is that we're looking at the stem here along the x-axis, the atom's filtration along the y-axis, and there's this whole other degree, the motivic degree, that's sort of suppressed in this picture. And in particular, these dots, like non-equivariantly, you would assume these were like FPs. Equivariantly, these are all like tau to the fourth tau squared towers that have different motivic weight and are coming out of the page. So anyway, the point is that you have to do like some careful degree analysis, which is more complicated because we have motivic weight and topological degree. But the point is you can conclude that no non-trivial differentials occur. So indeed, these phi survive the atom spectral sequence, and you get the splitting that you're looking for. It'll stop there.